This is Chemistry 302, lecture number 5. This lecture is an introduction to the topic of chemical equilibrium. We have spent the previous 4 lectures looking at this thing we call physical equilibrium. You'll notice that the word equilibrium is used in both of those statements, physical equilibrium, chemical equilibrium. What that means is that from a thermodynamic perspective, we're at a place where delta G is equal to 0. And this suggests that in terms of what's going on in a process, whether it's a physical process or a chemical process, the answer is, on a macroscopic scale, not much is going on. The difference, though, between physical equilibria and chemical equilibria is that now we're actually going to start looking at chemical reactions, reactions in which we break bonds and form bonds and create these balanced stoichiometries, where we can say, oh, I'm exploding a hydrogen balloon. 2 hydrogens, 1 oxygen makes 2 waters. You have a balanced stoichiometric chemical reaction there. When I talk about that reaction being at equilibrium, I talk about it in the context that after all is said and done, looking at the chemical system that's involved, it doesn't appear in the snapshots that I take of that system that the number of molecules of hydrogen, of oxygen, and of water are changing at all. They're all staying approximately the same. Now, of course, we know that in the same way we say about physical equilibria, say at a phase transition where you have a liquid becoming a gas at the same time a gas becomes a liquid in this dynamic to and fro, back and forth, but overall nothing's happening, but boy, a lot of stuff is happening on the atomic scale. The same thing is true with chemical equilibria. We will be sitting at a place inside this system where on the macroscopic scale nothing is happening, but on the molecular scale, molecule by molecule, atom by atom, you're actually seeing the situation in which you have a process going to the left at the same time that you have a process going to the right. Overall, nothing's happening, but on that molecular scale, it's a very busy world. So I'm going to go ahead and give you an example of this idea in action using the most famous kinds of chemical reaction that I do, which is exploding a hydrogen balloon. So let me go ahead and write this reaction down here for you. It's a reaction in which hydrogen and oxygen react to make water. Now, having written this down here, I can see what my molecules are that are involved, but I also know that there's some stoichiometry going on here, that I've got to balance things so I have conservation of mass. And there's my result. 2 hydrogens and an oxygen make 2 waters. Every time you watch me light off a hydrogen balloon and it explodes, this is in fact what's going on. How are you taught to think about this traditionally? You're taught to think about this such that over here on the left side you have these reactants, and over here on the right side you have products. So that's always the way it is, reactants, products. That is actually quite the misnomer, because the truth of the matter is that, as we learned when we were looking at thermodynamics, there's nothing that stops me from deciding that rather than look at the reaction in which hydrogen and oxygen go to make water, I might also want to be able to look at the reaction in which the reverse occurs, in which water goes to make hydrogen and oxygen. When we were first introduced to this, it was put in the context of whether or not a reaction was spontaneous or not, whether or not delta G was positive or negative. And we talked about it such that we would say, in one direction the reaction happens, delta G is negative, and the other direction the reaction doesn't happen, delta G is positive. And so we stopped at that point and said, this is a nice way to write this. This is a nice way of showing that the reaction can go in either direction. But then even at that point, we just made the assumption that the reaction happens from left to right. What we actually will learn when we start looking at chemical equilibria is that there's a different way to draw this picture. It's a way to draw this picture in which I have this kind of well that I've established here. Down at the bottom of the well is a place where the free energy difference is 0. So on this free energy scale here that I've drawn, right down here at this point, nothing is happening. By that I mean for every hydrogen and oxygen that react to make water, I've got a couple waters reacting to make 2 hydrogens and an oxygen in this kind of back and forth process. That's what's happening down here. Well, what's happening up the sides here? What's happening up the sides is dependent upon whether you're on the left side of the curve or on the right-hand side of the curve. If you're on the left-hand side of the curve, you're starting off with a bunch of waters, a bunch of hydrogens and a bunch of oxygens. Maybe I've got 100 hydrogens and I've got 50 oxygens. And what are they going to do? Well, what they're going to do is they're going to fall down this potential energy hill. What I would say then is that they're going to fall down this hill such that the hydrogens and the oxygens react to make water. But how much water are they going to make? Are they going to make all water? Am I going to get to a point where down here at the bottom of the hill I have 100 waters and no hydrogen and oxygen? That would suggest that this reaction has gone to completion. That would suggest that every bit of this becomes that. And what chemical equilibria tells us is that that is not what happens. The hydrogen and the oxygen are going to react, and as they react, they're going to make water as they go down the hill, down, 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 till they get to right here. At that point, there will be in the container certain amounts of hydrogen and oxygen and water in equilibrium, but it will not be all water or all hydrogen and oxygen. Well, similarly, we could start over here on the right-hand side of the reaction and say, what if I just started with a bunch of water and said, ready, set, go, and let it react? Well, it would react in the opposite direction, heading back this way, falling down to the bottom of the hill. Notice that both sides of the reaction, as they fall down to the bottom of the hill, fall to the same place. They fall to a place where there is the equilibrium amount of the hydrogen, the oxygen, and the water. The question you might ask, though, is what is that equilibrium amount? How will I know when I've found it? The answer is that equilibrium amount is going to be equal to the ratio of the stuff that's on the right-hand side, the water, to the stuff that's on the left-hand side, the hydrogens and the oxygens. See, that right there is my equilibrium ratio of the concentrations of what's on the right to what's on the left. That value K is what everything tries to reach at the point where delta G is equal to 0. Now, I can find out what K is by looking it up in the back of the book, and we'll learn plenty over the course of the rest of the semester about how K is found and what typical values for it are. But what I want you to know right now is that as we look at this expression here, we have to understand that it is now arbitrary to talk about a reaction being reactants on one side and products on the other. The truth of the matter is, how you start is stuff on the left and stuff on the right, ready, set, go. And then you let it happen. And whether it's cascading from here down to the bottom or whether it's cascading from here down to the bottom doesn't really matter. The key thing in the end is that at the bottom, it will get to this thing called K.